first ever artificial satellite to enter the Earth's orbit. Sputnik 1 was launched by the Soviet Union in 1957 and was the size of a beach ball. Sputnik 1 was followed by Sputnik 2 that carried the first living being into Earth orbit, a dog named Laika. And today we have thousands upon thousands of satellites traversing space. Let's understand a bit more about these man-made satellites or man-made moons. A satellite can be considered as a lighter body that revolves around a comparatively larger and heavier body in an orbit. The Earth satellites are objects which are revolving around the Earth, and the motion is very much similar to that of the planets around the Sun. We can say that Kepler's laws of planetary motion are equally applicable to satellites as well. Usually, their orbits around the Earth are either circular or elliptic. The Moon is the only natural satellite of the Earth with a near circular orbit and a time period of approximately 27.3 days. This is equal to the rotational period of the Moon about its own axis, which is why we always see the same side of the Moon in the sky. But there are lots and lots of man-made satellites revolving around the Earth as well. There are currently over 3,000 active satellites orbiting the Earth. The size, the altitude, and design of satellites depends on their purpose. A man-made satellite is a machine that is launched into space and orbits around a body in space. Examples of man-made satellites include the Hubble Space Telescope and the International Space Station. Now, consider a satellite that revolves in a circular orbit at a distance of RE plus h from the center of the Earth. Here, RE is the radius of the Earth and m is the mass of the satellite and v is its velocity. The centripetal force required for this orbit is given by F centripetal is equal to mv square divided by Re plus h. Now, this force is directed towards the center. The gravitational force is given as F gravitation is equal to capital G times small m times capital M sub e divided by Re plus h whole squared. Now, we know that me is the mass of the Earth. Equating the above two forces, we get the relationship v square is equal to gme divided by Re plus h. And from this relation, we can conclude that as the velocity decreases, the height increases. So the higher you are, the slower you will move with respect to the Earth. Now consider a case where the height is 0 or your satellite is moving just above the surface of the Earth. The value of v square is obtained as v square is equal to capital G times me divided by Re, where small g is equal to capital G times me divided by Re squared. In order to determine the time period of the satellite, that is the time taken by the satellite to complete one revolution around the Earth, let us consider the satellite covering a distance of 2 pi Re plus h divided by the velocity v. The time period therefore becomes equal to t is equal to 2 pi bracket Re plus h divided by v. Now we have already calculated velocity earlier. Substituting that value of v in this equation, we get the square of time period as k times Re plus h whole cube. Now this might remind you of Kepler's laws, and that's not a coincidence, because from this relation we can see that Kepler's law is applicable here just as it is applicable to the Earth around the Sun or the Moon traveling around the Earth. Imagine a case where the satellite is still pretty close to the Earth. So close in fact that the value of h above the ground is very small compared to the radius of the Earth and can be neglected. In this case, the time period is given as t naught is equal to 2 pi under root Re divided by g. Substituting the values for g and Re, we get the value of 85 minutes for a satellite. So that was the time period. Now, in order to calculate the energy of the orbiting satellite, let us consider the kinetic energy of the satellite in a circular orbit with a velocity v as half mv square, that is equal to g capital M small m divided by 2 Re plus h. Now, the potential energy of the satellite is given as Pe is equal to negative times capital G times small m times large me divided by Re plus h. The total energy is the sum of the kinetic energy and the potential energy. That is, the total energy is given by the value Ke plus Pe is equal to negative G small m Me divided by 2Re plus H, and thus the total energy of the satellite is actually negative. Now this can be a bit confusing. What is the meaning of saying that the energy of a satellite is negative? Let's understand. Even though the potential energy and kinetic energy vary from point to point for an elliptical orbit, the total energy remains constant. Consider the significance of the statement. The total energy of a circularly orbiting satellite is negative. We can say that if the energy is positive or zero, the object will escape to infinity. We know that satellites always move at a finite distance from the Earth, and the energy cannot be positive or zero. This means that the satellite is bound to the Earth through the gravitational attraction of the Earth. Let us summarize what we have learned so far.
Manorama Horizon. Learning made simple.